Hello and welcome. Today we're going to be looking at a TMUA style question about a set of triple logarithmic simultaneous equations. So you can see we're given these triple simultaneous equations in A, B, and C. We're told that A, B, and C are positive and that they're all not equal to 1. And then we're asked which one of the following statements about the solutions to the system of equations is correct. So either the equations specify A, B, and C uniquely, so they have one unique solution for A, B, and C. The other possibility is that the equations specify the product A, B, C uniquely, but have infinitely many solutions for A, B, and C. Or we could have that one of A, B, and C are specified by this set of equations, but there are infinitely many solutions for the other two. And our final option is that the equations have no solutions. This problem is essentially asking us to investigate these simultaneous equations and figure out some things about the solutions. Now, one bit of information that's very important to spot is that A, B, and C are on the same side of 1. So I'll give you a little more detail on what I mean by this. Let's imagine that log base x of y is positive. So we could say log base x of y is equal to p, and that would then give us, if we took both sides to the base x, that y is equal to x to the p. Now, we are in this scenario because log base a of b, for example, is equal to c, and the question tells us that c is positive. Similarly, we can see that log base b of c is equal to a, so that's also positive, and log base c of a is equal to b, so that's also positive. So if we know that log base x of y is positive, what can we say about x and y? Now, there are two real cases to consider. So what happens if x is bigger than 1? And what happens if x is between 0 and 1? As for why these are the relevant cases, the log functions will behave significantly differently depending on whether the base is bigger than 1 or less than 1. So if the base is bigger than 1, a log graph will look something like this. But if the base is less than 1, our log graph will look more like this. We have a very different behavior. Let's look at the case x is bigger than 1 first. In this case, y is equal to x to the p, and p is a positive number. Now, since x is 1, if we take it to a positive power, we're going to see that y is also equal to 1. If instead x is between 0 and 1, well, x to the p is going to be a number between 0 and 1, taken to a positive power, and that's also going to be between 0 and 1. So what this means is that if log base x of y is positive, then x and y are going to be, quote unquote, on the same side of 1. This is helpful for us because we can see that log base a of b, log base b of c, and log base c of a are all positive. What this means is that a and b are on the same side of 1 by considering this equation, and b and c are also on the same side of 1 by considering this equation. So that will mean that a, b, and c are all on the same side of 1. So we have either a, b, and c are bigger than 1, or a, b, and c are all between 0 and 1. You'll notice that we skip this case here, where maybe x is equal to 1. Now, we don't usually let logarithms have base 1, because the only power of 1 is 1 itself. If you take 1 to any power, you will always get 1 back. However, in this case, they also tell us that our potential bases, A, B, and C, are not equal to 1. So we don't have to think about this case at all. So why are we doing this? The hope is that this is going to give us some extra information, which might help us either find some solutions or prove that there are no solutions. But before we proceed with this, there's something else that we can notice about these equations, and that is that they are cyclic. So what I mean by this is, let's suppose that A, B, C is a set of solutions. What happens if we shift everything to the right? So let's say we replace B with A, C with B, and A with C. Let's consider what's going to happen to these equations when we do that. So this equation over here, B is going to be replaced with A is going to be replaced with C, and C is going to be replaced with B. So we're going to get log base C of A is equal to B. This equation over here is going to become log base A of B is equal to C. And this equation over here is going to become log base B of C is equal to A. What you'll notice is that this is the exact same set of equations that we have above, just written in a different order. And what that means is that if A, B, and C is a solution, this set of equations we're getting by shifting the solution along by 1 is also going to satisfy the equations up here. So C, A, B will also be a solution. And by a similar argument, if we shift everything along by 1 again to get B, C, A, this is also going to be a solution. So we know that if we have this one solution, we get these other two set of solutions. So why is this helpful? Well, A, B, and C are just letters. So if we started with a solution, A, B, C, and shifted it along to get, for example, C, A, B, we could just rename these letters, A, B, C. Something important to note about A, B, and C is that they're not equal to each other. So if we supposed that, for example, A was equal to B, then that would mean that log base A of B would be equal to 1. However, log base A of B is equal to C, and we're told that C is not equal to 1, which means that A cannot be equal to B. And similarly, A can't be equal to C, and B can't be equal to C. The fact that these letters are not equal to each other means that there is a biggest one. And by shifting our solutions along and renaming, we can always assume that the biggest letter is the one on the left. So what we can do is assume that A is bigger than B and C. If you remember, we realized that either A, B, and C are all bigger than 1, or they're all between 0 and 1. So let's look at this case by case. We can have our first case be that A, B, and C are all bigger than 1. Now, if we look at this equation, log base A of B is equal to C, we can take both sides to the base A to get the corresponding equation B is equal to A to the power of C. Now, since A and C are bigger than 1, we have a number that's larger than 1, and we're taking it to a power which is larger than 1, which means that A to the C will be bigger than the original number A. From that, we can conclude, since A to the C is equal to B, B is bigger than A. But this is a contradiction. This can't happen since by shifting things around, we've got to the case where A must be bigger than B. Let's look at the second case. We can try A, B, and C being between 0 and 1. By the same argument, we know that B is equal to A to the C. However, in this case, we instead have A and C between 0 and 1. What we have here is a number A, which is between 0 and 1, that we're taking to a power C, which is less than 1. And what this is going to result in, again, is A to the C being bigger than A. So, again, B is bigger than A, since B is A to the C, and we have another contradiction. So, if we look over our working, we can see that we've only made logical steps. So where could we have gone wrong? Why are we reaching these contradictions? Well, the only possible false assumption we could have made is that there is a solution in the first place. What we've essentially shown is that if there is a solution, we can take a set of logical steps and reach something that mathematically is nonsense. In both cases, we're showing that A is bigger than B, but B is also bigger than A, and that's not allowed. So the only possible conclusion from this is that the answer is D, and there are no solutions. Okay, so this was quite convoluted, but we did get there in the end. I do want to stress that there are lots of different ways we could have got this contradiction at the end. The real important thing is to realize that A, B, and C have to be on the same side of 1, and then use this to look at the two different cases and set up some inequalities. It's not necessary, for example, to, like we did, shift things around and assume that A is the biggest. You can always look at each case, try to set up some inequalities, and eventually you're going to find that some of those inequalities start to contradict each other. So I would encourage you to attempt this question on your own, see if you can find your own method. Best of luck with that. Thank you so much for watching. I'll catch you all in the next one.